Let us understand how we can reduce the work input in the compression process by using multi-stage compression with intercooling. And let us do that with the help of this PV diagram right here. Let us say you want to compress from a pressure of B at state 1 to a final pressure of A, right? You want to reach from B to A. Of course, the pressure of A is much higher than B, and you can do that in two steps. You can do that in two ways. Sorry, you can either do it in a single step. That is, you can go along the path 1 to 2 dash, and when you do that, the work input that's required for the compression process, it's what is given by the area 1 2 dash A B 1. So this is the area that I'm sketching in red. That is needed. That is indicating the work input that's needed to achieve this compression. Now you can also achieve the same compression, or you can also achieve the same pressure at the exit of the compressor by going along another path. Okay, so instead of compressing everything in one stage, you could do that in two stages. So you compress from a pressure of B to an intermediate pressure PI, right, in the first step. So this is what you do in the first compressor. Then you cool down the gases. Okay, you cooling this down because you want to reduce the specific volume, and the specific volume is something that you would want to reduce because work input is integral VdP. Now the delta P is same. If you can reduce specific volume, you can reduce the work input that's required. Anyway, so you cool it down to a low temperature, and then you do the second compression stage, and it takes you eventually to the same pressure. So you go from a pressure of B to PI, and then PI to a pressure A, which is what we eventually wanted. But here, the work input that's needed to achieve this is as shown in green. So the difference between these two processes is that in the second process, where we are doing multi-stage compression with intercooling, we are saving some amount of work, which is shown by the shaded area that I've highlighted here in red. Okay, that's the amount of work that we're saving by intercooling. So this is a very smart way, and this is one way that is implemented in a lot of gas turbine power cycles to reduce the work input for compression. So you have multi-stage compression with intercooling. Same way, if you want to do the opposite, if you want to increase the amount of work output while expanding between two given pressure stages, you need to increase the specific volume. And you do that by doing the multi-stage expansion with reheat. Okay, now you can do multiple stages of expansion, right? More than 2 stages, more than 4 stages, depending on how much you would want to do and how much it makes sense. But the concept is very similar, right? And it'll simply increase, it'll maximize the work output per unit mass. Of course, I'm not saying that this is something, I'm not saying that 4 to 5 stages happen in practical systems. In practical systems, it's usually 2-stage compression and 2-stage expansion with a single reheating stage. All right, that's the most common approach used, again, because it is a perfect compromise between economics and thermodynamics. So these are the two other changes that you can make. And certainly when we're talking about regeneration, you know, when you combine regenerative or when you combine regeneration with intercooling and reheating, well, the thermal efficiency and the network output both increase. And this is one way in which the overall efficiency and the work output can increase and thereby give you a smaller footprint for the turbine with the same net power output. Okay, so this is one of the most common modifications in earlier turbines where you're limited to very low temperatures relatively low temperatures in terms of the turbine temperatures that we're talking about. All right, so that completes this part right here. Again, if you want to look at what's happening for a case with multi-stage compression with intercooling, multi-stage expansion with reheating, please go through example 9.8. The example that we're going to solve, or the problem that we're going to solve in the class, involves all of these things, all of the modifications happening together. And this is one sketch where you have all of these things together. You have regenerator, you have two-stage compression. So you have compressor 1 and compressor 2 with an intercooler in between to reduce down the temperature. And in most cases, the temperature after reduction, T3, right, which is the inlet to the compressor 2, is usually kept equal to T1. That's how we sort of cool it down, right? And then you have two-stage expansion, right? Turbine 1 and turbine 2 with a reheater in between, just like we have seen in the Rankine cycle as well. Again, a common approach is to use the temperature in the second stage turbine to be equal to the temperature in the first stage turbine, although you can have T8 could be smaller than T6, but yes, T8 is equal to T6 is one common values that are used. Now, we said, well, we need to have two-stage compression and two-stage expansion. The question here is, what should be the intermediate pressure, right? What should be the pressure of the intercooler, for example? What should be the value of P2, and P3? What should be the value of P7 and P8, right? P7 is equal to P8, but what should be the value of P7? So here, the most optimum value, or the value which minimizes the work input to the compressor while maximizing work output from the turbine, is when you ensure that P2, P3, right, which are basically the same thing, is equal to P1 times P4, right? Or P2 by P1 is equal to P4 by P3. That is, the pressure in each stage is the same, both during the compression stage, that is, and also the pressure in each turbine expansion stage is the same. So if you ensure that this is the pressure reduction in turbine 1 is equal to the pressure reduction in turbine 2, well, this is going to give you the maximum work output from the turbine. Same way, if you ensure that the pressure increase in compressor 1, the ratio of pressure increase in compressor 1 is equal to the ratio of pressure increase in compressor 2. Again, you're going to get the minimum work input required to go from P1 to P4. Okay, and that is the main part that we're looking at. So why do we get at this specific values? Well, you can refer to example 9.1 where the derivation is given. You can also look at chapter 6, which we covered in ME 203, where they derive and show why this particular ratio makes sense, right? The last concept that I want to discuss here is about the combined gas vapor power cycles. Okay, now we have said that we always want to keep on increasing the efficiencies, and we have looked at several modifications to do so. Now, this is one last modification which allows us to increase the efficiency a little bit more. Okay, now this modification is called as the combined gas vapor power cycle, or just the combined cycle. And when we talk about combining gas power cycle as the high temperature cycle with a vapor power cycle as the low temperature cycle, the most common combination is basically what's done between the Brayton cycle, which acts as the high temperature cycle, right, and the Rankine cycle, or the steam turbine, which acts as the low temperature cycle. So this is a combination which gives much higher thermal efficiency than each of these cycles individually. Now, it makes a lot of engineering sense, if you think about it, to take advantage of the high temperature that you have at the exhaust of the gas turbine and to use it to heat up the, to take care of some of the heating requirements of the steam power cycle, or the vapor power cycle. And this is basically what is done in the combined cycle, as we will see in a bit. So the combined cycle, in the sense of temperature of heat addition and temperature of heat rejection formula, has a very high temperature of heat addition, simply because we are making use of the gas turbine as a high temperature cycle, and it has low temperature of heat rejection because we're making use of the vapor power cycle as the low temperature cycle. Now, this combination is increasingly used across the world, and even in Saudi Arabia, Aramco is converting a lot of their individual gas power plants to a combined cycle power plants, or individual steam power plants to combined cycle power plants, to achieve much higher efficiencies. And when we talk about efficiencies, real world efficiencies approaching 50% are even reported. So this is a very efficient system. Let's see how it works. So as we said, we are having a gas turbine combustor, which is a high temperature cycle, as the topping cycle, whereas the steam cycle, or the vapor power cycle, as the low temperature cycle. And the reason we say high temperature and low temperature is simply because the turbine inlet temperatures here are much higher, maybe 1400 Kelvin or even higher, whereas the turbine inlet temperatures for the steam turbines are much lower, about, let's say, 600 degrees Celsius, so 870 Kelvin, let's say, 873 Kelvin. So the advantage of this combination is that the high temperature exhaust gases that come out from the turbine can be used to heat up the steam or to generate steam within the steam generator. So basically, instead of having a separate boiler, we basically make use of the enthalpy of the exhaust gases coming out from the turbine to heat up the water and convert it from saturated liquid or compressed liquid to a superheated vapor, and that's what we expand within the turbine. So if you look at it, the net power developed the net power that is developed by the combined cycle is basically the power developed in the turbine of the in turbine 1 of the gas turbine cycle and the turbine of the vapor power cycle. Okay, so we're sort of getting two outputs, and the heat input is happening at only one place, which is this gas turbine combustor. So the thermal efficiency is the work output of the gas turbine plus the work output of the vapor power cycle divided by Qn. Now, when we're talking about ideal situation or an ideal or an adiabatic heat recovery steam generator, so here we are assuming that there are no heat losses to its surroundings. All the heat transfer occurs between the hot fluid and the cold fluid. And if you apply an energy balance, you simply are going to get that the enthalpy gained by the vapor, m dot v times h7 minus h6, is simply equal to the enthalpy lost by the hot fluid, which is the gas turbine exhaust, and it's going to show up as m dot g h4 minus h5. Now we're going to make use of these two concepts that we have discussed and solve problems in the class on Tuesday, as well as maybe it'll extend to Thursday. That's it for me. Thank you very much.